record. We had, what was her name? Is it Michelle Morse? Morse said she wanted to come, but she couldn't come, so I'm going to record me talking for her. Okay, so let's see if this is actually going to, oh, there we go. So the plan here, I'm going to go through introductions and whatnot, why we're here, and I'm going to talk for as long as I can about what I'm doing with innovative teaching methods, and then Jeff is going to talk about what ITS is doing to help implement different classroom technologies, since I wasn't able to get anybody else to talk. So I'm going to try and fill up an hour, and then we can just have open discussion if we want. It actually really doesn't matter how long we take, so until people tell me to shut up.
You did notice that the faculty administrator meeting is scheduled in here at 2 o'clock.
It shouldn't be. Christine told me this room was free, and it's booked on the calendar until 3. So okay. If she double booked it, it's not my fault.
I'm just warning, because it's what all the announcements have said going out, is that
really?
the faculty administrator meeting is going to be in here, up here. So just
fair enough. I really don't. I doubt we'll go until 2. So I think we'll be okay. Okay.
Take it away, Lisa.
All right. Okay, so probably you know from all the email blasts I've given about why we're here. So the point of this group is so that we can share innovative teaching methods. I was able to give a little talk during convocation in Klamath Falls about some of the classroom rearranging that we've done in the physics room, and it was surprising the response I got, because there was a packed house in that room in Klamath Falls, and they've I think created at least three rooms in Klamath Falls with sort of these group cluster arrangements, and they become so popular that they're just getting booked up, and they want more of them.
Yeah, we're up to,
is that true, Travis?
Yeah, we're up to 4 now. It might even be more next term. We'll see.
That's fantastic. Yeah, and in the room, there were so many faculty who were very excited by this and were really interested in having access to a room like that. And so I was sharing what I've done in physics. And as far as I know, the physics room is the only room currently that has this like group stout cluster seating. And for people that know of it, they've also been very excited and want to use my classroom. So this is a really important thing for me to be able to share with you guys, so that we can maybe spread that around around here in Wilsonville. There's obviously a lot of equipment stuff. Hopefully Jeff can touch on that in his talk, about ways we can use technology to make some of these innovative teaching methods easier. And so that's really what I hope we can do as a group, is kind of discuss some of those methods and how to make them easier to implement. Because sometimes that's the biggest obstacle, is you hear about this new approach here and just like, the time it's going to take to implement that is what's preventing me from doing it. So other things we might do, we could do journal clubs, we could do workshops here, like if, lesson planning sort of workshops, or we could go to conferences or other things off-site for workshops. So that's the plan. I guess it really depends on the involvement of you guys. So if there's people here, so far so good. We have people that are interested in being involved, so that's great. All right, so I don't have to talk. This is what I like to do in my classroom, is not talk as much as possible. So I'm going to make you guys talk for a little bit. You can tell everybody in the room what your role is here, why you chose to attend, and if there's anything on the last slide about what I hope this group does that you want to add to, feel free. And I'm going to pick on Aaron because he walked in late.
Well, in my defense, I was getting pizza ordered for a recruiting event at PCC.
And so that your sound shows up on the microphone, you can talk into the microphone and then pass it along.
Hello, everyone. So my name is Aaron Shear. I'm a faculty member in the EERE department, and I'm here because I want to learn and share and collaborate on new teaching methods and active learning in the
I'm Grant, and I'm here because I'm a one-trick pony, and I have one agenda in my world, and that's to get a teaching classroom with video. And it looks to me like ITS has finally stolen the money and is going to go a different direction. So I'm here to lobby to get the faculty on board so that we can have real teaching rooms that we can do inter-campus and remote. And so, sorry to be such a dull one theme kind of guy, but that's why I'm here.
It's okay. That's a good theme to have.
Hello, I am Chris Rosenberg. I am IT program faculty here and program director. In my previous life, I was the chief information officer for a number of universities and specifically focused on educational technology and teaching techniques using technology to make learning outcomes more successful. So I'm interested in contributing any way I can, as well as learning to see what other people are doing in their classrooms, in particular teaching techniques that maybe are not as technology driven, but are still more effective ways of teaching and learning.
I'm Jeff, I'm the network administrator here. I'm here to help with solutions to teaching problems using technology. Also here to make sure that the entire campus is represented for different strategies, and I interwork with a lot more instructors and faculty than most people here. So maybe somebody has a project that they're working on that someone else is already working on as well. It can hook them together, or maybe someone's already even solved whatever the other person's trying to do. Say, does this solution work for you? And save a lot of people a lot of time, a lot of money, and also, increase the use of technology here where it seems appropriate.
He's also here to keep certain people apart.
All right, I'll take a seat so I'm part of this circle. Okay, so I'm faculty here and I teach physics, currently just the introductory physics sequence, and I started this group, so that's why I'm here. And I wrote the mission statement, so I don't have anything to add to it. All right.
My name is Paulo Vasconcelos. I'm a graduate student in the Renewable Energy Engineering program, and I think that the reason why I'm here is just because I came from the undergrad, and I can try to give a student perspective of what will be the type of labs that we have here, type of teaching methods that we have here. And now that I was working with some of the faculty here as graduate teaching assistant, I'm kind of moved from the student role to more close to a faculty role, and I was also invited to be adjunct faculty here teaching one of the labs in our power electronics lab. So I think that I can provide this range of perspectives and just to help to grow our university.
Howdy, my name is Matt Search. I teach generative writing here. My educational background, before I got into the line I'm in, has been in instructional systems and instructional design. And I commit to doing new and interesting things in all of my classes every single term. I'm here right now because this is the first CCT meeting in 5 years that has not been scheduled when I'm teaching. So,
Yay.
so cool. Keep it up.
I'm Dawn Taylor, and I'm with the Clinical Laboratory Science program. And I guess what interests me most in coming and being part of the cohort on Wilsonville is just interest in adult education and new and innovative things and learning what people are doing on this campus and in Klamath Falls. And specifically the implementation part. I have heard a lot about different methodology, but kind of get hung up with the implementation. And so being able to share with others in what they're doing and how they're handling things, I think is going to be really important.
Okay. It was just like my class. Well, thank you guys for allowing me the opportunity to not talk the whole time. Okay, so what I'm going to talk about for a little bit is what I've been doing in the physics classes here, and then the flipped classroom approach is where I'd like to go. I'm not doing that quite yet. So what I've implemented in order to do group learning, the first step was upgrading the classroom arrangement. So I'll talk about that, and then some of the different teaching techniques I've been using, and then the flipped classroom approach. Talk about that. Yes. Okay. So I was hoping that I had a picture of the physics lab before I made changes, and unfortunately we didn't take a before picture. And there's a few rooms on campus that have the terrible fold-out tables that I used to have. They don't slide very easily. They just tip right over. Those terrible chairs that just get hung up on the carpet. That table right there, that's the kind of table. And so as far as rearranging the room, it was a giant mess. And so it was just lecture-style seating crammed as far back towards my lab benches as possible. And then I had 6 computers on top of the lab benches with all the equipment in the drawers below. So imagine 18 students smashed up against those lab benches, trying to use the computers, and people trying to get into the cabinets all at the same time. And then Mateo said, I'm going to increase your class size to 24. And I said, I literally don't have 24 seats. Like, I don't have 24 seats. So we'll pretend that I said, wow, this is a fantastic opportunity to innovate and come up with a better solution. And I did get there after a little while. I did my little pouty dance, but then things went smoothly, and Richard created these tables very, very cheaply for me. So I have 6 tables, very industrial looking. They're on roller caster wheels that lock, so I can move them around if need be. The biggest expense were those chairs. So the tables were the cheap part, because we were able to use stuff we already had. And the chairs, I insisted that if I'm going to have 6-hour classes, my students need comfortable chairs. And so Mateo agreed, thankfully, and my students really appreciate that. Okay, so there's another view from the other side. And you'll notice that we got rid of the 6 stationary computers that were on the back bench, traded them to IT for refurbed laptops. So that's a win-win for everybody, because Jeff said I can use these desktops somewhere more effectively, and I'm not using these laptops, so go for it. I didn't need anything fancy, so it works really well. I don't even have to lock them up because nobody wants to steal those laptops. So it works really well. At first we had the computers sitting on the lab benches, and it was the monitors were taking up a lot of space, and students were having trouble seeing around them. And so those laptops are stowable. You can completely clear off the tabletop and do the experiments right there in your group instead of having everybody clustered around the back bench. You can actually take the laptops and roam around the campus and do experiments wherever you want, which I love. You'll see those posters hanging in the back. You can't read them, so the next slide is going to show what they look like up close. So that's another innovative teaching method that I implemented around the same time that I rearranged my classroom. So some of the teaching techniques I'm going to touch on. So the group-based learning is been big, where I push a lot of the activities to the team clusters that I now have. The patterns approach physics, those are the posters I'm going to show you. We've got a lot of different things on campus, resources on campus that I'm trying to get my students aware of by getting them out of my classroom and using them. And then I do more project-based learning and then some online activities. So it's just a smattering of the different teaching techniques that I've been working on, trying. Some work and some don't always work. So some of the group-based learning, how that looks now that they're in these clusters, I start the lesson with a review, concept review questions. So these are multiple choice questions. They're not super problem solving based typically. I want them to just be concept based. And the reason I implemented this is actually interesting. We had to do one of those ISLO reviews of 222, which is the electricity and magnetism section of physics, which is, everyone knows that's the hardest term of physics that everyone takes. And it was very eye-opening because we found out we were evaluating students' scientific reasoning skills and problem-solving skills. And we found out that students, over the course of the term, develop very good problem-solving skills. But this is across both campuses. Students were abysmal at the scientific reasoning part. They were not understanding the concepts. They were just find the tool, see if it worked. Okay, it worked, but they don't know why. And so that was our idea. We needed to incorporate more concepts into the lesson. So that's these concept review questions, that's the main goal. And just doing that alone, I saw students' understanding of the fundamental principles, the terminology, that just exploded. So that was all I needed to bring that component of their understanding up. Something I tried are these concept-rich problem-solving type problems. University of Minnesota has this thing called cooperative problem solving. That's for these group sort of situations where you assign very specific roles. They have a very structured way they have to go about solving the problem. They all do the same very complicated problem working in a group. It's the kind of problem where even in a group, they're not going to be able to solve it. So it didn't go quite how I hoped. Students really hated it. The part they hate the most is being assigned roles. Like, they're happy with the fact that they would get a role, but they want to pick their role. They don't want you to tell them what role they have. So I tried that out, and I've tried to keep components of it, but the way it's implemented at University of Minnesota, I don't know that I'm sold on it. There's a link there, so any of the links in here, if you guys think are interesting, I can send you my PowerPoint. There's also some context-rich problems that you would see like on an ACT exam, where you get a whole page sort of describing the setup. There might be a table, there might be a graph, and then there's a series of 6 multiple choice questions where they have to analyze data. I love those. And it's funny, I will just grab straight from ACT exams. So students presumably should already know how to solve these problems, but they're still challenging even at the college level. And then other things we do in the groups is they'll do some examples from the book or problem solving. And I've tried to get away from doing a lot of that on the board. I'll demonstrate a few times how I go through problem solving so that they get a sense of like what a good setup looks like, how to show their work. But once I've done that, a few times I really want them to be practicing it in class so that I could be walking around and making sure that they're getting those pieces before they go home. I want to see a good diagram. I want to see a good setup. I want their equations very clearly written before they jump into the math. And so that really just requires them doing it, the practice piece. Them observing me solving problems has been shown to be, the research shows that that's really not an effective way for students to learn. As much as they like seeing it, you can't just show them that and expect them to learn how to solve problems. So I think it's 2 years ago now, I took a class over the summer at PSU. I think it was taught by a high school physics teacher, and his approach is called the patterns approach. And so this is very specific to physics. The first 2 weeks of physics, what we do are 4 hands-on experiments. They're called inquiry-based labs. So instead of giving them a set of very detailed instructions, you ask them a question, you pose the question to them. So for the first one, I'm not really telling them what the goal is at all. I just say, okay, I have a spring, you see it here. I have this mass, you see it here. Using your understanding of how the world works, what do you guess this spring is going to stretch if I hung the mass from it? How far do you think it would stretch? And so they just make a wild guess. And then I said, well, what do you think the behavior is for this spring if I did different masses? So they make a couple hypotheses, and they do a graphical hypothesis, a verbal hypothesis, maybe even an equation hypothesis, so they can understand that there's different ways to describe a hypothesis. And they completely come up with the methods of the experiment. So as a class, I say, well, how would you test that? So it's a very open, those inquiry-based labs are very open to the students driving the experiment. And you kind of lead them down the path without them really realizing it, And then they do it, and they collect data, and they plot it, and they come up with a pattern. And then we talk about, they don't know it, but I've given half the groups one type of spring and half the groups the other type of spring. And we all look at everybody's graphs and say, well, what's the same and what's different? I call that the board meeting, because we all look at their graphs on the board.
Is this before you introduce even, force and?
Yes. Yeah, and the goal isn't to get a physics concept. It's not to understand the physics of spring. The whole purpose of the patterns approach is actually just to remind them of the math they should already know. And so after they've seen this, I say, well, what's this pattern called in math class? And so we say, okay, y equals mx plus b. You've seen that before. That's called a linear pattern. From now on, anytime you see an equation where it's got a y equals mx plus b or y equals mx type format, you now know it's a linear thing. And we're going to call it that. So throughout the term, I keep asking them, like when we get to force, I say, how does force depend on acceleration? And they should be at that point, oh, it's a linear relationship. And we do that with all of this. Linear they've got. I mean, they should have taken calculus, but it's amazing these fundamental math skills they just don't have. So quadratic, for the most part, they get. I get a little bit of the people wanting to call it exponential. When I get to the inverse, they really want to call it exponential. And when we get inverse square, the same thing. And so even when they see the equation, they see that equation plotted in logger pro, y equals a over x squared. I say, what's this equation called? And they say, it's an exponential pattern. I say, no, this is the exponential equation. That's an actual it's a quantitative idea, an exponential pattern. It's not a qualitative descriptor. And so part of it is training them away from these bad habits they've gotten into by calling things that they aren't. But these are the 4 most common patterns you'd see in physics. And you notice exponential decay is not one of them, because it really doesn't come up that often. In 221, these are the only patterns we ever see in 221. I don't do drag, right? So air drag, you'd see exponential decay, but I don't touch on that. So this is basically making sure their math is up to snuff, so that when I start talking about physics, I can keep relating back to these posters on the wall, and that makes it easier to make those connections later on. So this has been pretty successful. The only problem with it is it eats up 2 weeks at the beginning of term, and so then everything else kind of has to be compressed after that. So some of the other things I do is I've been trying to get them out of my room and to use other spaces on campus. Even with the group clusters I have, very limited space with 24 people in the room. So when we do a fluids lab, I actually go down to the fluids lab, which makes sense. There's sinks in there, and there's linoleum, and all the things that should be in a physics lab. So, might as well use that space. Scott Prawl has been very excited to incorporate my optics labs into his actual optics lab. And that's been really fun. So we kind of co-teach the optics lab in 223, and the students, not kids. The students get to see all the fancy equipment, and then I get to kind of sell them on the physics minor, because right now, if they do the physics minor, their upper level physics classes are all the optoelectronics classes. So they get a chance to play with the toys, and then I go, hey, you could do the physics minor if you like this. And then the other thing, I've been working with the 3D proto, or what do they call themselves, the club? It's not 3D printing.
No, Print 3D.
Print 3D, that's right. So the Print 3D Club has helped me set up, they do a tour of their prototyping lab and show off all their equipment. This is a YouTube video, so that link is a YouTube video of Jim Wilferling giving a tour. And then we do this at the end of 222 when they've learned circuits and thermodynamics, and that's like the perfect combination of the two. A very good application for all my engineers is a 3D printer. So they come up with a project that incorporates the 3D printing, and they've got to do some sort of, they got to make some connection to what they've learned in 222. So I love that. These projects I do are really student-driven instead of a typical lab where it's just, they get the set of instructions. They really have to drive their objective. And every group might do something different, and then they share with each other, so that's even better. So old school physics labs. You get these cookbook instructions, obvious outcomes. Usually students are not very engaged. And if they have other ideas about what to do, you say, no, that's not what we're doing today. We're doing this, and you need to do this. So what's happening is students aren't engaged in the material. They're not actually turning their brain on. And in fact, you get all these questions during the lab that if they would just read the instructions, they would know, but they're not actually engaged in the process. And it's almost like once they are given a cookbook style lab, if there's one thing that's like slightly different, they shut down. They're like, well, the lab said to do this, but it's, open this folder, science with Vernier on Logger Pro, but I see a folder called physics with Vernier. I can't do anything anymore. What do I do? So their brains are just off. They're just waiting for someone to tell them what to do. So that's really bad. And then they're not excited about the lab. They go home and then they realize they actually collected the wrong data and they didn't even realize it because they weren't even paying attention while they were collecting data. So they're really not learning anything from those labs. So an example would be an electromagnetism lab. They're going to follow the instructions, they collect data, but they don't really understand why they did it. And then when they get home to analyze the data, that's when I get the flurry of emails where they're like, I don't think I got the right thing. And I'm like, oh, okay, we're going to have to come back in and recollect data because you're right, you didn't get the right thing. So what I do now for an electromagnetism lab is I start with 2 concept building experiments, and I've been working on trying to get away from the cookbook and have it be more, they drive, sort of like those patterns-based labs where I give them a setup question and then they drive how they're going to conduct the experiment. And then it ends with a project, which they really love. So they have to design, build, and race a vehicle powered by a hand-built electromotor. So you might not know what that looks like, but an electromotor is just windings of wire placed over top of a magnet or 2 magnets and then connected to a battery. And so it spins, but it's really thin wire. And they find out really quick how challenging it is to actually get any sort of torque from this thin little wire. So then they start having to iterate their designs to see if they can actually get that wire to turn anything else, to power a car. So they first, as a class, decide what the race rules are. Like, what's the distance? Is it based on how long it takes them to get a certain distance, or who can get to a certain distance first? Whatever the rules are. I even had a class say, I was going to say, you can't spend any money. Like, you have to use all recyclables. And they were like, no. How about this? They called it like a $5 buyout, where they could spend whatever money they wanted on their car, but if I wanted to buy their car for $5, I could. So if they were willing to dump $100 in their car, it was money down the drain because I could just buy it for $5. So I let them decide the rules, and they're given 3 weeks and they've got to come back to me and show me that they're working on designs and whatnot, and then that they're following a scientific process and not changing 2 things at one time. Because you never know which one caused the outcome that you saw. And then they race, and they loved it. The race day video, I'll actually show it if I can get my mouse to appear.
There it is.
Just have to go slowly. We did this down in the cafeteria and probably scared a lot of people because they're not used to so much excitement on campus. And that was part of the fun, is like, we need more of this on campus. Students out there doing stuff, being excited about their classes. There's sound.